Hi, everybody. Welcome to this crash course in CalFat simulation. I invited myself to Thermo-Calc to learn a bit more about how it works. I brought two alloys that I'm working on or have been working on in my daily life to see if they could calculate on it with the Thermo-Calc simulation software, and it turned out pretty well. But take a look in this episode where Nicholas from Thermo-Calc has accepted my challenge and given me a crash course. Enjoy the show. Hi, Nicholas.
Hello, Peter.
Welcome to the podcast on everyday metallurgy.
I'm very happy to be here.
Yeah, and thank you for the invitation. I invited myself because I have talked to a lot of people about CalFET and Thermo-Calc, and they said a lot of words, and I didn't really know what it is. So I dig deeper into it, and therefore I contacted you because I would like a crash course on Thermo-Calc.
Okay, fantastic.
And I hope that you can give me a crash course in 45 to 60 minutes.
Great. I'll be happy to do it. Yes, I'll be happy to do it. Yeah. I hope you learned something.
Yeah, me too. uh, I would like first a little background about you.
Okay.
Um, well, your educational background, where you work.
Yes. Yeah, with pleasure. Okay. So my name's Nicholas Grundy. I have a PhD in, I'd say, CalFAT assessments. So I did database development, not for steels, but for oxide materials. But that was now a long time ago, more than 20 years ago.
Ooh.
Um, and my PhD I did with Thermo-Calc. So Thermo-Calc in those days didn't have a nice graphical user interface. It was just a black screen, and you interacted with a sort of a console mode script way. So after my PhD, I actually went and did a postdoc to another software company, well, to another university where they developed FactSage. That was the McGill Polytechnic University in Montreal.
Mhm.
So I've also been like a different type of CalFAT software. After that, I mean, the big decision, should you go to research or should you go to industry? And I decided to go to industry. And then I worked for the steel industry for about 10 years, for the SMS group. This
Mhm.
was, which is an equipment supplier
Yeah.
for the steel industry. And I
Mhm.
worked there as a metallurgist, mainly, I'd say, on developing or and commissioning continuous casters, but also had a bit of contact with electric arc furnaces, ladle furnaces, so steel refining. Yeah, and then about 7 years ago, I got a telephone call from Thermo-Calc, which has
Mhm.
grown into quite a big company by then.
Yeah.
And they were looking for people who have practical experience, but also background in CalFAT and
Mm.
Thermo-Calc. They asked me if I want to join, and I've been with Thermo-Calc ever since, and having a very good time, actually. Yes.
Fantastic. Great journey.
Yeah.
Yeah. Uh, Nicholas, can you give a short introduction? What is going on in the program like Thermo-Calc?
Yeah. Okay.
Just
So
two
I'll
minutes introduction
okay.
to thermodynamics.
Yes, this will be tough. This will be tough to do it in 2 minutes. But okay, so the first thing I have to say is that CalFAT is a method, and Thermo-Calc is the software.
Hmm.
And Thermo-Calc is only one of several softwares that are based on the CalFAT method. And to put it very simply, the CalFAT method is a way of looking at thermodynamics. And what you do is you give mathematical functions or descriptions for the Gibbs energy of all the possible phases that can form in a system. So let's take a simple duplex steel where you've got austenite and ferrite. So austenite is FCC, ferrite is BCC. then basically what CalFAT does is it gives a function of the Gibbs, a mathematical function that describes the Gibbs energy of the FCC phase in function of composition and temperature, and a second function that gives the Gibbs energy of the BCC phase in function of temperature and composition. And those two functions are independent of each other, right? It's a phase-by-phase approach. So each phase has its own Gibbs energy. And then what the software does, Thermo-Calc, is it very simply just minimizes the Gibbs energy and finds, because if you're in a minimum of Gibbs energy, that's the stable state. Everything will move towards minimum Gibbs energy. So by minimizing these the Gibbs energy of FCC plus BCC, you can predict what will be not only the phase fractions but also the phase compositions at equilibrium, and that's what it is. So inside Thermo-Calc, there's these CalFAT databases, and they're nothing other than Gibbs energy functions of all phases that can exist in a system. That's it. It's as simple as that.
Yeah.
It's as simple as that.
Yeah. And my experience, I've been melting in my previous life, is that in a melt phase or in a gas phase, you can reach equilibrium.
Yes.
But in 99% of the solid state phases, you never really see equilibrium, but you see something close to.
Absolutely. Yes. And if I may already answer your question now, because I'm very happy you actually said that, because this is something we hear very often, that, well, CalFAT is interesting, but it's only equilibrium, right? It's equilibrium and you never have equilibrium and so on. But I think the important thing to say here is that it's actually a non-equilibrium. You can calculate non-equilibrium states, and this is extremely important. So let's go back to the case of a duplex steel where you have FCC and BCC, or austenite and ferrite. Because you have both Gibbs energies described of austenite and ferrite, right? And you, for example, you solidify the steel and you're at equilibrium, fine, and then you cool. Let's say you're in the FCC state and you cool that down quite quickly into a temperature where BCC becomes stable, right? Then what you can do with Thermo-Calc is you can say, what you do is you suspend the BCC phase. So you say, okay, I've got the description of the Gibbs energy of it, but I don't allow it to form. And I've only got, I've got the FCC phase. And then I calculate the thermodynamics just of the FCC phase. And then I can calculate the driving force for formation of BCC, right? And this is this is probably even more important than equilibrium thermodynamics, because then at a low temperature, I've got the driving force for the formation of the BCC phase, and with other kinetic tools, let's say Dictra for diffusion or Prisma for nucleation and growth, I can then calculate together with the mobilities how fast these phases that want to form, how fast they actually form, right? Because I've got the driving force, right? And then the other thing I need is diffusion, and then I've got it. But you're absolutely right. I mean, and if you do those diffusion calculations, I mean, let's say for steel below 600 or 500 degrees, nothing happens. It's frozen in, right? The state is frozen in. But you can also do frozen in calculations, right? So you can assume that it's frozen in at a high temperature and then see what happens at low temperature. You've got all the driving forces for these phases that might form. And that's, I think, the like sigma phase that you don't want, right? Or carbides that you don't want, and so on. And you calculate how long will it take for them to form? Will they ever form? Is a risk that you have sigma formation, and so on. So that's it's that's what you can also do.
Yeah. I have prepared two cases that I would like to challenge you on.
Okay.
So the first one is it's a steel that I made many years ago. It's a high alloy tool steel, and we had some difficulties in the melt phase with that steel. So I would like to give you the chemical composition and if you will show me what you do on the run,
Yes.
you could share your screen and then
Perfect.
then we can try to see how it works.
Right, we'll do that. Yes. Okay. So I mean, and I'm excited to see how this will go. Right. So what I'll do here is I'll share my screen. How do I share? And I'll put it on my second screen. Is something happening?
Yeah, I see small climbers on a wall.
Okay, very good. Okay, so I'm just starting Thermo-Calc and I'll drag it over. Can you see Thermo-Calc program there?
Yes.
Great. Okay, so tool steel, and basically, I mean, this is what Thermo-Calc looks like when you start it up. And basically, we've got a window here on the left where you set up your project, and then a big window in the middle where we'll set up all the calculations. And on the right here, there's like a visualization for plots and things. And for me, I actually always start with just a single point equilibrium calculation. Or if it's something I don't know, like more about it, just start with a single point equilibrium, just so I know where I am and what this is, right? And then if I click on that, he automatically sets up the calculation that consists of a system definer. This is which I'm sitting on now here. And I've got the steel database selected. This is that CalFat database that I explained in the introduction, right?
Yeah.
So that's just a collection of Gibbs energies, but there's more in there, of course. It's not quite as simple. But for now, just let's say Gibbs energies. And on this periodic system, I've got all the elements that are available in the database. And if those elements are not like for example, gallium or indium are not in the steel database, and that means I simply can't make calculations with those elements. There's no way of adding them right on the fly in the software. You're stuck to the elements that we've assessed and that are in on that periodic system. Okay, so then if you could just tell me like which elements you've got and what the composition is, and I'll set it up on the fly and see what happens.
Wonderful. 2.8% carbon.
Okay, so obviously we've got iron. It's a steel based. Okay, so carbon, and this is all in weight percent, right?
Yeah, 2.8 weight percent.
2.8. Okay.
7 chromium.
Chromium. Okay. So then we go. And you see what I do? I just click on the periodic system, and then it appears in this list, and I can put in the mass percent. Okay, 7% chromium. Yes.
Yeah. 2.3 molybdenum.
Okay, so find molybdenum. 2.3. Okay.
Yeah. 9% vanadium.
Vanadium is here. 9%. Okay.
0.7 manganese.
Manganese.
And 0.8 silicon.
0.8 silicon. Great. Okay, so this is definitely, looking at this is definitely a high alloyed steel, right? It's got a lot of carbon, a lot of vanadium. Okay, so let's, okay. So then, I mean, basically that's all I have to do here in the system definer, right? He'll then search what he's got in those elements, put together the database in a form that he can use it for later calculation. And there's nothing more that we have to do here. Then we can move on to the equilibrium calculator. And as said, I usually, for something like this, that I don't, well, I can imagine what happens, but I don't know. So I just do a single point equilibrium just to see what we get, right? And it's already automatically set up for me, 1000 degrees Celsius, which I think is fine. And the composition, it takes over from previously. And then all you do is just hit perform. That's it. And then, well, here I've got the event log, and the software just tells you what he's doing, right? So he'll first read the database. These are all the references that are used in the database. So he reads the database and puts together all the Gibbs energy functions. And when he's done that, he should start setting up a calculator, and and that was quite quick. So, I mean, this is why I want to set them up live, right? Because that was 6 seconds, right? So a calculation like this takes the orders of magnitude of seconds,
Okay.
right? And then you've got the results here as a table because it's a single point calculation, right?
Yeah.
And he just gives some basic information, like I've set the system size to 1 mole. I could also set that differently to 1 gram or 1 ton. The total gives energy and some information, the overall composition, the activities of all the elements there, and which phases that I have at 1,000 degrees. So equilibrium, stable phases at 1,000 degrees. And you can see we've got FCC-A1, a volume fraction of 78%. So that's 78 volume percent FCC
the majority
A1.
is.
Exactly, yes. And then it also gives you the composition of that majority phase. And you can see it's a bit over 90% iron, 5% chromium, silicon, manganese, hardly any vanadium and carbon there. So where's the vanadium carbon gone? And you can see that it's got FCC A1 number 2. And FCC A1 number 2 has, let's look at the mole fraction here, because this is
almost half.
Exactly. So this is obviously vanadium carbide, right? So it's almost 50 mole fraction of 50 mole percent vanadium, 50 mole percent carbon. And in addition, we've also got some M7C3, so which is basically a chromium carbide, one of the famous chromium carbides. Everybody knows them. And again, it's not just chromium 7 carbon 3, right? It's got quite a substantial amount of iron in there. So it's not a pure M7C3. Okay. And now I think we have time, because again, this is somehow also giving background on why certain things are in certain ways. And I'd just here like to mention that the stable phases, we got FCC-A1 and FCC-A1 number 2. Now, what does number 1 and number 2 means? That basically means it's the same phase. It's the FCC phase. And then we've got an underscore, and A1 is the Strukturbericht, basically, which is one way of designating the crystallography. And so what this means is that this is basically the same phase. It's FCC A1, but it's got a miscibility gap between the, let's say, the carbon poor side and the carbon rich side. And like, and this is actually the correct way of looking at it. In like, normally metallurgists would say that FCC-A1 is austenite. They would say that's austenite because it's FCC iron. And FCC-A1, they will call that an MC carbide or a vanadium carbide. But basically a vanadium carbide, so this vanadium carbide is just austenite with all the interstitial sites filled with carbon. That's what it is, right? And there just happens to be a miscibility gap between austenite and austenite with all the interstitials filled with carbon, right? And that's how it's described in the database, right? So that's what it is. Okay.
And this is at 1,000 degrees.
This is at 1,000 degrees, yes, exactly, yes. And then obviously, I mean, you were mentioning about casting and solidification.
Yes.
So, I mean, what I'd do then is I've seen that the calculation works. I'd just do a one-axis. I mean, again, handling of the software, I've set up the calculator here. What I can do is I can just sit on it and say clone. So I make a second calculator, but now instead of a single point, I do a one-axis. And then again, don't go down to 0 degrees Celsius, because that's ridiculous, right? It's meaningless. Equilibrium calculation at room temperature is meaningless. So let's go maybe down to 600.
Yeah, that's fair.
And we go up to 1600. Or I'll even go to 700, because we're interested in high temperature.
Yes.
And then basically what I'm doing is I'm just stepping in temperature, and I click perform. He won't read the database again because he's already done that. So he'll just do the stepping calculation. Now that again should, okay, here's stepping, and that's it. And then I can just sit in the calculator, right click, create a successor, a plot renderer. And I mean, he automatically gives me the most reasonable like plot what I'm interested in is volume fraction of phases in function of temperature and perform.
Yeah.
Right.
Mm-hmm.
And this is what I get. Right.
Exactly.
And now we can have a look at this result for a little bit. Like what I sometimes like doing is I like maybe just to put the scaling to 1.1 perform, right? So you can just see. So at high temperature, 1600 degrees, it's pure liquid.
Yes.
Right? If I hover over, it's liquid. And then this solidifies basically and forms FCC A1, which we've learned is austenite, and FCC A1 number 2, which is vanadium carbide, more or less at the same time. There's a bit of a vanadium carbide here forms a little bit above the formation of the bulk matrix phase, and I can, by the way, I can just zoom in there like that. But it's 20 degrees higher, so that's
not a lot.
Nothing to be worried about at all. And then you start, once it's fully solidified, you start forming M7C3 carbide. The austenite decomposes to form not the normal ferrite perlite, but ferrite plus this M7 carbide right here. And then the M7C3 carbide at low temperature decomposes to M23C6. So but again, if you cool this fast, I mean, it's not necessarily that these phases will form. And just a last word on this calculation is that I mentioned the Calfat method is all about Gibbs energy, right? But right now, actually, if I look at, if I just click on this and have the drop down of all the things I could plot here, you can see that we've moved on from just describing the thermodynamics. We've now got things like, let's go down. The density, right? So we've got the density of the material. Let's just for fun, let's click on density. There you go. See, okay. I'm automatically scaling it from 0 to 1. The density is higher than 0 to 1, so I can't see anything. But let's see if that helps. Perfect. Okay.
There we go.
Yeah, and so this is the density. You can see how density increases. Then on solidification, and then actually when the austenite decomposes, there's quite a significant drop in density there, but the density and so on. So just quickly going through these density, we've got viscosity of the liquid. We've got the elastic constants, right? This is something that we are adding since recently into our databases, right? Young's modulus, bulk modulus, shear modulus, electrical conductivity, and electrical resistivity, but also thermal conductivity should be here somewhere, down here. Thermal conductivity, thermal diffusivity, because of course you've got heat capacity, and surface tension of the liquid. So it's much more than just thermodynamics. Okay, but let's go back to volume fraction of phases. But honestly, volume fraction of phases, you mentioned that you had problems in casting powder production, right? And in this result, there is nothing to suggest this should actually work very well. This has a narrow melting point. This should work very well. There is nothing here that would suggest that we should have problems.
No, Now the story comes.
Now comes the story.
Yeah. When we made this alloy, we were atomizing it, and we had difficulties in the alloy clogged in the nozzle. And then when I opened up the nozzle and I made a microstructure analysis, I could see a lot. It was primary carbides, so a lot of MC carbides.
Okay.
So the vanadium carbide, as you see, has this arm into the melting phase. Yep.
Yeah.
But when I cut through one of these carbides and I measured the chemical composition in SEM ADAX, I could see that there was a substantial amount of nitrogen at the nucleation site inside the carbides.
Okay.
And then we went back and said, oh, okay, we are protecting the steel with a nitrogen atmosphere.
Okay.
Maybe nitrogen is an activator or an elongator of this arm, of the liquid arm. So it's not
Okay.
only 20 degrees, maybe it's because it's solidified at temperatures around 1500.
Okay.
So that was a bit difficult to
Okay.
understand.
Great.
So
Okay. So
can you add that this is in an atmosphere of nitrogen,
yes.
and then see what happens. So if we have
Yes.
an equilibrium with a melting phase and a gas phase of nitrogen.
Yes. Okay. So I think, okay, so I mean, that's a very interesting story. And I think it's
Mm,
also, I think, a message of hope there, I'd almost say, right? Because uh, this somehow means that again, if I was an artificial intelligence,
mm,
I would, again, I would have simply given you the answer, this won't clog, right? But of
mhm,
course, it's very important also to think about the process and what's happening in the furnace and just other things that could happen, right?
mm,
And I think the key word, as you mentioned, is nitrogen atmosphere, right? And if
mm,
you melt this in a nitrogen atmosphere, I mean, you have elements in here, vanadium, that have a high, let's say, affinity to nitrogen, right? So
yep.
it's known
Mm,
that vanadium nitride is potentially quite stable. Okay, so what I would do then with that additional information that this was actually produced in a nitrogen atmosphere.
mm,
So again, just like handling Thermo-Calc. So I'd have to set up a new calculation. And so I don't do everything twice. I just go in the system definer and say clone tree. So I then make a copy of the whole calculation.
yeah.
And
Uh,
and then importantly, add nitrogen.
mm,
Okay, and then I move on to the equilibrium calculator. And now, how do I set the condition for nitrogen, right? Because as you said, this is somehow like you're not adding nitrogen on purpose to the alloy.
mm,
It somehow comes from the gas atmosphere.
yeah.
And now, so the condition to set here,
Mm,
and for this I have to switch to the advanced mode. And
yeah.
if I switch to the advanced mode, I've got far more possibilities of setting up my system or setting up my conditions.
Okay.
And
Yeah.
the condition here to set is an activity condition.
Hmm.
And and so the activity of
Mm,
in the gas phase, because this
uh-huh.
steel is in equilibrium with the gas,
Yeah.
of N2 nitrogen.
Yeah.
And then let's say this is just, let's say it's air. So I put 0.2,
Okay.
0.8 there. I could
Yeah.
put 0.9 or whatever, right?
Yeah. Yeah.
Okay.
Hmm.
So this is an activity condition. And what
Mm,
that does in the background is these are high temperatures, right?
hmm.
So we can assume that the gas phase will decompose, like all the molecules of the gas phase will decompose into, let's say, their equilibrium constituents. So
Mm,
the N2 will partially dissociate into 2N, right?
mm,
Two
yeah.
atomic ends.
Hmm.
So that might be active and might find their way into the steel, right? And
Mm,
these calculations work at high temperatures, right? Or realistic at high temperatures, because at high
yeah.
temperatures the
Mm,
gas phase is in equilibrium, you can say. And you
mm,
can also assume that there's an equilibrium of nitrogen between the gas phase and the liquid metal, right? This is the condition of thermodynamic equilibrium, that
mm,
activities of a certain element are the same in all phases. That's a
mm,
definition of thermodynamic equilibrium. So
yeah.
if we fix the activity of the whole system corresponding to this gas that contains
Hmm.
80% nitrogen, that will
Yeah.
also fix the activity of nitrogen at whatever it is, right? Because we don't, and this is another thing. So we don't have to worry about nitrogen activity, like the activity of atomic nitrogen, right? We just have
Hmm.
to give the composition of the gas phase.
Yeah.
And Thermo-Calc internally, he handles all that, right? He knows what the activity of atomic nitrogen is, because he knows the equilibrium constant of N plus N equals 2N. He
Mm,
knows that, and he just right? You don't have to worry about activities ever if you use a
Okay.
software like this, right? And again, I'll actually, and let's say you're trying to melt this at 1500 degrees, and I'll stick to my principle and just always start with a single point equilibrium, just to be on the safe side, and click perform.
Yeah.
So again, that's what, and now let's see what happens. Now, because I've added nitrogen, he has to read through the database again. He has to reassemble all the functions.
That's
Then he
fair.
does the calculation, but again,
yeah,
should be a couple of seconds.
As I remember, we were also able to measure the nitrogen content in the steel afterwards.
Okay,
and
interesting.
we were some way above 1000 ppm.
Interesting.
So more than 0.1%.
Okay, perfect.
So
great. Interesting. I mean, this is why it's exciting also for me. Right, we didn't discuss all this in advance. I had no idea that you had measured it. So it's exciting to hear that and to just to see how well the calculation compares to whatever you measured, right?
Yeah.
So, but the first thing, I mean, this is somehow expected, right? So I did the calculation at 1500 degrees, and at 1500 degrees, you can see that I've got this FCC A1 number 1 here. Now it's called number 1, but it's vanadium, not carbide as it was, but it's a vanadium carbonitride.
Yeah,
and you've got, it's got 1%, right? It's a significant volume fraction.
Yeah, and it didn't exist at all before.
Yeah, exactly. No, absolutely. And now let's have a look how much nitrogen moved into the steel. And here you can see its mass fraction 0.002. So this is actually even 2000 ppm. So factored in equilibrium, it's factored 2 higher than what you measured, right? And again, this is again the important thing, right? Do you achieve thermodynamic equilibrium? And I mean, I would be very surprised if you achieve the thermodynamic equilibrium content of nitrogen in the liquid steel if it's in contact with an atmosphere, right? Because here there are things that I know from electric arc furnaces and from ladle furnaces, how much nitrogen does actually go into the steel. And I mean, you have a phase interface there, you've got the liquid, and then you've got the gas phase. And so the nitrogen somehow has to move to that interface and also has to move through that interface to go into the steel, right? And it's actually known that nitrogen pickup is determined both by thermodynamics, but also by mass transfer or by transfer through that interface. And it's known to be very sensitive to things like oxygen content in the steel or sulfur content in the steel. And because these change the surface tension of the liquid metal, so how much nitrogen actually goes in there is strongly determined by kinetics. But still, I mean, you measure 1000, that's halfway towards
more. We measured above 1000. I don't
even
remember
above,
it was 1200 or 1500, but it was high.
Significant. Okay, great.
But we also did two things that enhances the take up. One, it was an induction furnace, so it was induction steering. So the steel was circulated like that.
Okay.
And furthermore, when we cast it, we didn't pour, but we had the teapot method. So we put a lid on and we pressurized it with nitrogen. So the deeper we went, the higher pressure. It was maybe a partial pressure on 1.2 bar instead of 0.8.
Oh, okay. Okay.
So we did a lot of bad things to the steel.
Okay. Great. Yeah. I mean, let's just quickly do a one. I already set up a one axis because now I'd be interested to see, of course,
how high does it go now?
Exactly. So let's just do a one axis calculation there.
Yeah.
I went up to 1600. I hope that'll be enough because it was there in good quantities. And I've also, still got the old calculation so we can compare directly. Okay, so that's the old calculation. And now the new one. What's happening? Okay, so don't worry, the low temperature, I'll hide it here a bit because these are mainly sort of numerical things that I would have to figure out here, what's actually happening. I also see graphite forming, right? And this is...
might not.
No, exactly. And this is typical. I mean, even a normal steel, right? Graphite is the stable phase, right? So, but that would be a typical phase that you actually have to remove from the calculation. So you go into the system definer here, you go to phases, and you go through all the phases there are, and then you find graphite somewhere, and then you where is it? Graphite, CTE, graphite. You just remove graphite, right? Because you know for kinetic reasons that doesn't form. Okay, and now also to make it maybe a bit nicer, I'd like to change this from linear to logarithmic. 1 e minus, let's say 3. So volume fraction. Right. And then you can see that this carbonitride actually forms just above 1500 degrees, and quite significant. And if I just compare that to the, again, make this one logarithmic as well. Just 3, say 2. So I've got the same scaling. Right. So this is without nitrogen, and this is with nitrogen. So it's a huge, huge stabilization of the just go backwards and forwards, stabilization of that vanadium carbonitride. Yeah. Okay.
So and I can disclose what we did because we found these nitrides and said then nitrogen might be the cause of our problem. So we installed an argon tank, and we changed our protection gas and our pressurizing gas to argon to avoid the nucleations, and it worked. So we never had problems again.
Perfect. Yeah, perfect. It's a nice example. Honestly, it's a nice example because it's very clear from the calculation what the problem is, right? It's very clear. You immediately see that, right? Vanadium nitride is, and by the way, I mean, the other thing, things like titanium or niobium are even more stable, like nitride formers. So, I mean, if you have impurities like that, then that can also cause problems in many cases.
We made a trial with a 10% niobium alloy.
Okay.
And that was difficult, even with argon.
I can imagine. Yeah.
Because the niobium carbides were also very stable at a very high temperature.
Absolutely. Again, if we had time, we could look at niobium as well, but
Yeah, but thank you for the first one. Then, wow, that was fantastic to see how you could use Thermo-Calc to calculate on liquid phase in metals. And in this case, I tried to trick the process, but I couldn't. He could reproduce what I expected, so that's very nice. But we'll make a break here because I have another case. In the next case, we will look into if you could use Thermo-Calc to simulate on kinetics, because we will look into an alloy where precipitations will occur when you heat treat it at pretty low temperature. So it's a stainless steel with copper precipitation, and I was wondering if you could use Thermo-Calc for that. But take a look at the next episode when it comes out. It will be pretty interesting. See you soon.